So let me introduce the next speaker is Ivan Bozovic. He's a very distinguished scientist working in Brookhaven National Laboratory. And he will talk to us today about the road to room temperature superconductivity, 3 lessons learned from cuprates.
Good afternoon, everyone. I'm Ivan Bozovic. I work at Brookhaven and at Yale University. I regret of not being able to join you because we are still under travel restrictions to conferences, even both international and national. It's still an honor to talk to you today, but it is also a challenge because high temperature superconductivity, and even more so the room temperature superconductivity fields, have been tarnished with a lot of hype in media circus. And when you mention one or the other, it frequently triggers in people a negative reaction. The message that we should take home, therefore, is that hype aside, this is legitimately one of the most important open problems in physics of our times. Here is the outline of my talk. The key point I will try to make is that cuprates are not exciting just because of high TC and of prospective applications, but even more so because they profoundly challenge our textbook understanding of superconductivity and of metallic conduction. I will try to keep my arguments very simple, at the risk of oversimplifying, for which I ask the expert to forgive me. So a little bit of a glance back. The textbook chapter on metals was largely written by 4 authors. It was initiated by Paul Drude, who modeled metal as an electron gas contained in a can. This model was refined by Lorentz, quantified by Sommerfeld to account for the Fermi statistics, and finally put on firm theoretical grounds about 60 years ago by Landau, the so-called Fermi liquid theory. Here I have singled out few details that will prove to be important what will follow. They come from the existence of the Fermi surface. Because of that, only a small fraction of electrons of the order of kT divided by the Fermi energy is available for scattering. And the low energy excitations behave as a nearly ideal gas of some effective quasi-particles. After many failed efforts, including by the likes of Einstein, Bohr, Pauli, Heisenberg, etc., the puzzle of superconductivity was solved eventually by Bardeen, Cooper, and Schiffer. Their key postulate was that electron-phonon coupling causes a weak, effective, attractive interaction that pairs electrons in the inverse space, in K space. These Cooper pairs are large. The partners can be more than 1,000 unit cells away, so the pairs overlap and they stay entangled. Again, I have singled out here a few essential details that are important to what follows. First, TC is determined by the dynamics, the electron spectrum, the phonon spectrum, and their coupling, or the interaction potential. Second, at 0 temperature, the superfluid density should be equal to the total electron density, and it is basically unrelated to TC. This and other aspects of theory of superconductivity were cemented by the Landau school, in particular by Migdal and Viliashberg. And importantly, Lev-Gorkov showed that BCS is an instability of a Fermi liquid. So the two go together. And they can. Now, many theorists have asked what would happen if we could somehow increase the pairing interaction strength. And the conclusion was that the pairs would become smaller and smaller, and the BCS physics would continuously cross over to Bose-Einstein condensation of compact non-overlapping pairs that behave like boson gas. This was just an academic point for many years, but eventually such a crossover was in fact realized experimentally in experiments with cold atoms, either by increasing the pair interaction strength, which they can tune, or by making the cloud thinner, thus crossing over from 3D to 2D behavior. So note that both of these facts, the high PC and the two-dimensional behavior, favor Bose-Einstein condensation over BCS. And important, once you are beyond the crossover, insofar as TC is concerned, the strength of the pairing interaction doesn't matter anymore. It's kinematic. It's the boson density that matters. I should also point out that all known superconductors have resided in this left BCS corner. Now, let's come to the cuprates. So, for condensed matter physics community, discovery of huge high temperature superconductivity in cuprates was something like the eruption of Vesuvius, or perhaps more analogously like a flying saucer landing at the Times Square. In 1986, I was at Stanford working with Ted Ball, and in November we learned that Bednorz and Miller have discovered superconductivity in cuprates with TC of about 30 Kelvin. For this, they received the Nobel Prize in '87. Now, the insider know that the nomination for the Nobel Prize closed on January 31st. So it took just a couple of months from the first disclosure to the public to multiple and compelling nominations. Something like this happens perhaps once in a century. This by itself would tell you that this was a first order importance event in physics. In strontium cuprate, resistivity is linear in temperature till at least 1000 or 1100 Kelvin. This is another major puzzle apart from the very high TC. This was, in fact, reported already in '87. Remarkably, it's still true. What is shown here is an LSCO films grown by atomic layer by layer molecular B epitaxy in my lab. And note that residual resistivity ratio is at least 200 for those who synthesize sample. That is better than in any bulk LSCO single crystal. Essentially, the residual resistivity is zero. The important point is that this T-linear dependence was not expected from the textbook Fermi-liquid picture of metallic conduction. And I will split this into two. Apart from the T-linear dependence itself, there are two other major discrepancies. The first one is that, unlike in the standard metals, the resistivity does not saturate at high temperature. And it should, since the mean free path cannot be smaller than the distance between the atoms. There is nothing to scatter electrons on. This is known as the Joffe-Regge limit or Mott-Joffe-Regge limit. And this limit is grossly violated in cuprates. This is colloquially known as the bad metal behavior. There is another, maybe even more upsetting discrepancy, and that is that in Fermi liquid at a low temperature, phonon and other excitations should die out, and the electrons only scatter elastically on lattice defects and impurities. Now, lanthanum strontium cuprate contains strontium dopants, which are charged impurities, so they should be pretty strong scatterers. Electron is charged and there is a Coulomb repulsion or attraction. At optimal doping, the average spacing between this charge defect is about 8 angstroms. One would not expect the mean free path to get much longer than that. But actually, resistivity does not saturate at low temperature. It keeps decreasing way below this Fermi liquid expectation. It is called in the field the paradox of the missing elastic scattering. It seems that elastic scattering on charge defect is absent. So in London-Strontium cuprate, the temperature dependence of resistivity looks both strange and bad, without any clear separation between the two. Note that the slope remains exactly the same all the way up to 1000 Kelvin, without any jumps or kinks. My guess is that at least in cuprates, the two are one and the same. And this linear dependence is so simple that, as Jan Zanen once said most eloquently, some powerful principle must be at play. Let me just mention in passing that at very low doping, when 1-trans-strontium cuprate becomes an insulator, it remains very strange as well, perhaps even more strange. And my guess that this is also originating from the same powerful principle. Now, what is the microscopic explanation? Well, countless theories have been already proposed. There is no time to go through all of them, or even briefly. So there are a lot of ideas what could be causing this bad and strange metal behavior. For an experimentalist, the question is how to differentiate between them, how to refute the theories that are wrong. And my answer is that we should study systematically the dependence on pretty much anything that we can vary: disorder, doping, magnetic field, frequency, direction of the current. And then we should also compare lanthanum-strontium cuprate to other cuprates, look at other properties other than resistivity and magnetoresistivity, and then look at other compounds, and maybe learn something from these systematic dependencies and comparisons. So let me start with dependence and disorder. This is a systematic experiment of the study of the effects of disorder that we did about a decade ago. So what we did is we picked up an optimally doped lanthanum-strontium cuprate film and then irradiated it with 1 mega electron volt ions. We did this in a combinatorial way. So we patterned the film into 32 pixels and then exposed each pixel to a different dose, which was exactly known. And that gave us a combinatorial library of 32 samples, each with a different irradiation dose and therefore with a different level of disorder. And the short of this experiment is that when we did the unbiased fit to the whole set of data for all the pixels, all the disorder levels and irradiation levels, we found that an unbiased fit to something that includes both parallel and series contributions, the fit inevitably turns two of these coefficients to be zero. In other words, it looks like a parallel connection of two resistors, one which has resistivity proportional to T, like strange metal, and the other T squared, like a Fermi liquid. This is sometimes called inverse Mathiasen rule. Phil Anderson called this anti-Mathiasen rule. So one of our listed Fermi liquid predictions fails. Let's look now at the dependence on doping. So here are sets of data for lanthanum strontium cuprates doped to very different levels. You can see that at high temperature, the dependence turns to be linear. At low temperature, high doping, there is more of a parabolic. Low temperature and high doping, there is more of a parabolic curvature. In the middle are some very recent systematic data that we collected on something like well over 1,000 devices and doping levels. To the right is the result of fitting to the serial resistor model. Rho equal to rho naught, the residual resistivity, plus a term linear in temperature, plus a parabolic term. And as a function of doping, this coefficient A, which is A1 in my formula, was found to decrease linearly and disappear right at the edge of the dome. I have some issues with this plot, one of which is that these are actually two ordinates. The TC, which is the dome, has dimension of Kelvin, while A has dimension of ohm over Kelvin. So you can change these scales arbitrarily. The one that is shown here is selected so that this straight line is a perfect tangent, but if I change the scale, I could make it be horizontal or vertical. The other problem is that some of these dots were from YBCU and thallium, and those actually have different domes from lanthanum strontium cuprates. But these caveats aside, what you can take home is that the linear contribution, the strange metal contribution, is actually decreasing as you go more and more over dop. That can actually be seen visually without any fitting from the figure in the middle. You see that the top one is pretty much perfectly straight line, and then the bottom one starts looking more parabolic. Now, I can also try to fit this by a two-component model. These are the same experimental data to the left, and to the right is simulation. So what I have done here is I have fixed the strange and the Fermi liquid components. The strange metal component is fixed to have the Planckian scattering rate, which is kBt divided by h. What I'm varying as a function of doping is their relative contribution. So the strange component is decreasing from 1 down to 0 at the dome edge, while the Fermi liquid component is increasing. And nothing else. You can see that there is striking similarity between the data and the simulation. Let me turn now to the magnetic field dependence. So in the literature, magnetoresistivity data are also typically fit to a serial resistance model, which will be applicable if you have a single carrier species that encovers two or more different sources of scattering. One of these has to give this linear in field dependence, which is mysterious, strange, unexpected in Fermi liquid theory. And you would need to explain that. But my point is that if you look carefully, this fit to the series model is actually not very good at low fields. And that should be obvious from the shape of the curve. It is parabolic at low fields and linear at high fields. And that's not what you get if you have x and x square in series. At high x, x square has to win. So you would expect linear behavior at low field and parabolic at high field. What we see is the opposite, and that points to a parallel connection, in which case the higher conductivity wins. And to the right is the fit to the parallel conductivity models. Now we could also look at both dependencies at the same time, temperature and field. This I cannot plot in 3D, but what I've done is to color code the measured resistance, and then to guide the eye, I have read the curves of the constant resistance. So you can see that at optimum doping, these curves are linear except near the axis, meaning for very small field and very small temperature. And this is not what would be expected, not only in Fermi theory, but also in none of the models that have been proposed in the literature. At the bottom, I have four cartoons. One is what would you expect if the resistance scale with the larger of T and B, or actually KT, the KB times T versus mu B times B. It would look like a rectangle. If we have scaling with the square root of the sum of the squares, this should be perfect circles. What we see are straight lines, at least close to the optimum doping. And that points to a simple summation of two energies, KB T plus mu B times B. That has several implications. One is that it looks like it is the energy relaxation that is relevant. So when you add frequency, you would expect also to add plus h nu. The second one is that the magnetic terms look like Zeeman, not like orbital effect. So it looks like a spin effect. And that is also supported by some observations that there doesn't seem to dependence on the rotation of the magnetic field. Okay, let me now go to the frequency dependence. This is work that we have done in collaboration with Peter Armitage and Fahad Mahmoud, who are experts in terahertz spectroscopy. And they have studied systematically the frequency dependence of the optical conductivity in a series of LSCO films grown by atomic layer by layer molecular beam epitaxy in my lab. Their key findings are as follows. First, the superconducting gap is not seen where it should be expected from BCS theory. Second, the drop of spectral weight starts at an energy that is as much as 10 times higher than the BCS value, indicative of very strong pairing interaction. And the third and most surprising is that the drop is only partial. The loss of superfluid density is only small, and it is the loss of spectral density is small. It goes into superfluid, and it's accompanied with the increase of a residual Drude-like conductivity due to normal electrons. And this is present even at temperature close to zero. Now, let's look at the dependence on the current direction. We have studied this systematically by using a new technique that is we call angle resolved transfer resistivity measurement. So we patterned the Armstrong-Kubrev films into a sunbeam pattern of 36 hole bars at 10 degrees from one another. and then we measured both the longitudinal and transverse voltage at many angles. We found that as a function of in-plane orientation, both the transverse and longitudinal resistivity showed oscillations with 2 periods and 4 nodes. The amplitude remains the same, but the phases are shifted by 45 degrees between transverse and longitudinal. This shows that the fourfold rotation symmetry is broken up to the room temperature and every doping, implying that the resistivity tensors is always orthorhombic. Note, however, that our films are strictly tetragonal. They are epitaxially pinned to a tetragonal substrate, and we have verified this by high-resolution synchrotron X-ray diffraction. Moreover, the orientation of the easy direction of high conductivity is not aligned with the crystal axis. It varies with doping, and it even rotates with temperature. This all shows that this anisotropy is essentially just in the electronic liquid. It's uncoupled from the lattice. And in modern parlance, this is called electronic pneumaticity. Of course, this could not happen in a gas or in ferroliquid, which is kind of gas of charged quasi-particles. Everything that I've said so far was about the metallic in-plane resistivity. The out-of-plane conduction looks incoherent and semiconductor-like. In cuprates, they are quasi-two-dimensional conductors. Indeed, we have many other proofs for that. The most direct is that superfluid density can be confined to just a single unit cell thick cuprate layer and still have the same TC as the bulk samples of the same material. We have amply demonstrated this over the years. And most recently, a couple of groups succeeded in cleaving visco crystals down to a single unit cell layer thickness and found that TC remained the same as in the bulk. Let's look at the other physical properties. We have studied systematically the key parameters of the superconducting state, such as the magnetic penetration depth. This is a plot of the superfluid density as a function of doping and temperature. It brings in several surprises. The first, this superfluid density is basically linear in temperature all the way to TC. This is surprising because in the BCS, the gap should close at TC, and we should expect some leveling close to TC. Second, as we increase the doping, the superfluid density should increase, tracking the carrier density. But what we see is the opposite. It decreases actually all the way to zero. And third, as we increase the doping, the superfluid density decreases all the way to zero. The temperature at the superconducting temperature is comparable to the superfluid stiffness, which is superfluid density expressed in Kelvin. And note that the two are about the same, and which means that it is extremely low. In niobium, the superfluid stiffness temperature is more than 1,000 times higher than TC. This means that in cuprates, the superconducting transition is controlled by thermal phase fluctuations. Now, we can read the dependence of TC on the zero temperature superfluid density, and this is how it looks like. It is smooth and essentially linear, but with a finite offset, except close to the origin when it turns to a square root dependence, as one would expect for quantum critical phase fluctuations. Let me point out that almost identical dependence was seen in a different cuprate YBCO by a different group and using a different technique. Moreover, it was on the heavily underdoped side. This is critically important. YBCO and LSCO have very different electronic spectra. In YBCO, the electron bands from the two nearby copper oxygen planes are close to one another. They hybridize into bonding and anti-bonding combination, and they split, and they are populated to a different level. The phonospectra are also different. and the electron-phonon coupling calculated using DFT differs by 300%. Last but not least, LSCO is overdoped and YBCO underdoped. And yet, the TC versus superfluid density relation is essentially identical. One does not expect this from BC. One would from BC. We have also tried to measure the charge of the carriers above TC in collaboration with Doug Nathanson at Rice University, who is the leading expert in shot noise measurements. And here is the result, the key result. The red line shows the superconducting gap region. We see that a large fraction of electrons is paired even way outside of this region, along both axes, not only well above TC, but even about twice the superconducting gap energy. This is quite shocking. In the normal state, a substantial fraction of charge carriers is paired, therefore bosonic. It looks like a new state of condensed matter. Some people call this emergent Bose metal. This finding indeed strongly constrains the theory and may prove to be pivotal to cracking the high TC enigma. Other properties. You know that good metals reflect like mirrors, but in cuprates, this is not the case. There is strong infrared absorption and also electronic Raman continuum, both extending up to 1 electron volt and higher. This was first reported in early '87 when I worked in Terji Ball's group at Stanford. Moreover, the whole number is not really a number, but a function of temperature. The tunneling conductance is also strange, and so is NMR, nuclear relaxation, etc. Chandra Varma and collaborators pointed long ago that these strange properties are actually connected to one another. How about other cuprates? Well, YBCO, Bisco, thallium, cuprate, neodymium, doped lanthanum strontium cuprate, as well as N-type cuprates, praseodymium, cerium copper oxide, lanthanum, cerium copper oxide, all show linear dependence of resistivity on temperature and also on the magnetic field at high fields. I want to focus on this data for thallium, strontium, calcium cuprate, which is very clean. And here you can see something even stranger. If you fit to the series resistance model, you would get, or you simply extrapolate the high temperature linear in temperature resistivity part down to 0, you will get a negative intercept. And this, of course, makes no sense. But you can actually fit this very well to a parallel conduction model, in which case the paradox goes away. And this seems to be seen also in other samples once they're very clean. So I've seen this in a number of BISCO films and also in few of LSCO films. How about other materials? Well, here is a very partial list of other materials that behave like strange or bad metals. And that includes other oxides like iridates and rutenates, iron-based superconductors, including both chalcogenites and pnictides, magic angle graphene, some two-dimensional organic superconductors, etc. What do we conclude from this? Here is the list of the strange experimental facts. starting with resistance being linear in temperature and magnetic field, violation of both the Joffre-Regel and defect scattering limit and Mathiassen rule and Coller's law, the fact that C-axis transport is incoherent, electronic nematicity, pairs in the normal state, and other strange properties. But importantly, similarity to other strange 2D metals. So this is my first caveat, is that since all these materials show strange metal properties, this behavior seems to be much more generic than the cuprates. So it should originate from something which is not specific for high TC cuprates, like spin charge separation or quantum critical point at one-eye doping, but something, or room club scattering, but something that is very generic. It could be, for example, arising just from the Heisenberg uncertainty relation between energy and time, and the fact that we are at the limit of ultra-fast, essentially instantaneous energy relaxation and hydrodynamization, as Jan Zeman would argue. In any case, this is not quasi-particle gas behavior. And then by Gorkov's tenet, it means that the superconducting state cannot be of the BCS sort. This is then my proposal is that actually data could fit better a two-component model. The model, something like a parallel series of two conductors, one of which is strange, showing Planckian or hydrodynamic behavior, the other Fermi-liquid-like. With doping, their nature doesn't change, but the ratio does. The Fermi-liquid component grows at the expense of the strange metal fraction, which disappears at the edge of the dome. And nematicity also decreases with doping, and it seems to track the strange metal fraction. We also see the pair breaking rate, which increases with both temperature, magnetic field, and doping. And with the decrease of the strange metal component, this is mistake here, as the strange metal component decreases, TC decreases, and so does the superfluid density, while phase fluctuations grow until global superconductivity is destroyed. Caveat here is that this two-component electron-liquid model does not explain our central puzzle, which is what is the origin of high-temperature superconductivity in cuprates. It also doesn't explain what is the origin of the strange metal behavior. It only explains the evolution with doping on the overdose side, that is the crossover from the strange metal to the Fermi-liquid behavior, which may be specific to cuprates. But this fact 3 may encode some hints about 1, since it seems that nematicity, TC, superfluid density, etc., all scale with the strange metal fraction F. So here is my guess. We see large gap in cuprates. We generically see a large gap. In visco, it can be 100 millielectron volts, and we see pairs even well above that. That points to a very strong pairing interaction, and that points that we are not on the BCS side of the BCS-BEC crossover diagram, and that should explain the high TC. But then you can ask, why is the pairing interaction so strong? What is the microscopic origin? And here is my guess, that the pairing interaction is so strong because in cuprates what we have is a CO2 layer that behaves like a 2D metal, even if a strange one, and charged reservoir layers, which are ionic insulator layers. So it's essentially interface superconductivity, something that Vitaly Ginzburg predicted more than half a century ago. By the way, the same seems to be true also for iron-based or for nickel oxide superconductors. The second thing, which is probably unique to cuprates, is that the super exchange is exceptionally strong, and this comes from the degeneracy between the copper 3D and oxygen 2p orbitals, which is not true for any other oxide. Now, this was my guess. For more serious attempts, you can look at any or all of these theoretical approaches. I would say that the safe conclusion is that there is no consensus at all, and the season is still open. There is still room for someone to come up with a correct and universally accepted theory of high TC superconductivity, which will then enable us to predict where to find new and better high temperature and perhaps low temperature superconductors. So a glimpse at the future, how to differentiate, how to sort this out. And my answer is by comprehensive and meticulous study of a large set of the high quality samples showing intrinsic properties by state-of-the-art techniques, by systematic comparison and unbiased analysis. This task is beyond the capability of any group. It calls for large, coherent, organized, focused, and sustained effort, and I'm afraid substantial, sustained, dedicated funding. Just one glimpse, perhaps timescales could help. The time resolved pump probe experiments can help differentiate between electron-electron, electron-phonon, etc. interactions. And I mean not just by measuring the reflectance, but also measuring the structure by ultrafast X-ray and electron diffraction by time-resolved ARPES, RICS, and whatnot. And I would like to end here by dedicating this to Vitaly Lazarevich Ginzburg and to Ted Gibol, who regrettably is at the hospital right now, and perhaps.
Thank you, Ivan, for this very nice presentation. Yes. So the session is open for questions.
This over my lighthouses. These two people were showing me the light in the fog in theory and experiment. And we have missed Ginzburg, and we are probably going to miss Ted.
Thank you, Ivan. So the very interesting talk is open for questions. Okay, over there we start with.
Thank you. It's really nice talk. I have a question about this. Cuprate is very special, and copper oxide plays important role in the superconductivity. We learned something from the cuprate, and can we just use this, acknowledge our experience in the nickelates, or can we observe this kind of the same behavior only in the copper oxide layers?
Well, I can only speculate, and as I said, my speculation is that the two ingredients are essential in cuprates. One is that it is a native SIS, IS, MIM superlattice. And that confines the metallicity to 2 dimensions, which makes it strange. You cannot have coherence in 2 dimensions and not in the you cannot have Fermi liquid in 2 dimensions and not in the third one. The second is the very strong super exchange. Something has to be very unique and specific to the cuprates, which makes them have TC so much higher than any other materials, at least at normal pressure. And that seems to be the chemical fact that stands out, is that you have this degeneracy between the copper and oxygen relevant orbitals, and that gives this covalent bonding in the CO2 plane. This is not true to the same extent in nickelates. So super exchange is weaker. The interfacial superconductivity should be there also. Again, we're having metallic nickel oxide layers and sitting next to ionic, strong ionic insulator layers. So that should be present, but maybe the second factor is not present there. And the same are true again to some extent in iron superconductors. So there is similarity, and I think difference is in this detail, which probably determines or controls the strength of the pairing interaction.
Another question. Yeah.
Dear Yuan, thank you for your very illuminating talk. At the end, you mentioned pump probe experiment, but you know, the pump probe experiments were done and the results revealed a variety of interactions at the time scale spanning from femtoseconds to microseconds, from electron-electron type interaction to high energy phonons and then to low energy phonons. What would you more expect from this type of measurements?
As I said, you know, the key of what I was trying to say is this in this line A, which is the answer. We need comprehensive study, and in my language that means 1,000 samples, 3,000 samples, not one sample. That's how we studied, for example, the superfluid carrier density and resistivity and magnetoresistance. Second, you need samples of the highest quality, and that you need to reveal the intrinsic properties, that you're not masked by defects. Then you need state-of-the-art techniques. The reflectance pump probe measurements have been done long ago, but you know, that's just kind of like one number there. We could do much more than that. There have been one or two studies by ultra-fast pump probe electron diffraction, and also by X-ray ultra-fast pump diffraction, and these things are much more informative. And new things are coming, like time-resolved ARPES and time-resolved RICs, and maybe other time-resolved probes. So what I would like to see is a huge set of data where we have all of these parameters varied, and then things will pop up. You know, it's very easy to fit one straight line, like rho versus T being linear. Pretty much any model that has 3 or 4 enough open parameters should be able to fit that. But when you have all these variables, you get some kind of multi-dimensional, you know, surface in multi-dimensional space, and it looks like Himalaya mountains. It's very difficult to fit it with the model, even if it has 4 or 5 parameters, unless it is correct. So that would be that's what I'm hoping for. I don't see other way to convince everyone. single shot experiment convinces those who believe it already, but not no one else.
Yvonne, there are two questions from Zoom, from the internet. Do you see them?
No, but you can read those to me.
Okay, I can read them for you. Why R of t is assumed to be a sum of power law terms of integer power law exponents.
Oh, this is a good question. This is just a model. And again, if you restrict yourself just to rho versus t curves, these things are very simple. They are very simple curves. You can fit it with 2 or 3, polynomial of second order. You can also fit it with rho equal rho 0 plus a times t to b. This was done more than a decade or two ago, for example, by Leah Krusinelbaum, who is a very prominent researcher in superconductivity, and she showed that she could actually fit all these curves and the doping dependence that way. And what was changing in that case was basically the exponent. So exponent was changing continuously from 1 to 2. You can fit the data that way. What I was trying to say is look at the whole opus of data, not just at the resistivity versus temperature, but also resistivity versus flux versus magnetic field, disorder, dependence on frequency, etc. And when you put all these together, the simplest model I could put forward to kind of fit the data would be this one, for which there is some physical justification. The picture is that you have one component which actually shows this strong pairing. This could be, for example, the antinodal region of the Brillouin zone, where the band is very flat, and these things behave like a very viscous fluid and show this strange metal behavior. And the T-linear dependence has physical origin, which is Planckian dissipation that Jan Zanner was talking about, which basically means that energy relaxes so fast that elastic scattering of the momentum actually without energy relaxation never comes into play. So that has simple intuitive picture behind that. And then there is a Fermi liquid part.
Yvonne, just a second. We have 2 more questions and we really run out of time. Shall I tell you the questions?
From the nodal
just for a very short answer, or sorry to interrupt, but one seems to me very that's something a bit provocative for you, or that could be interesting for you to answer. That's why I'm interrupting.
Please.
Can I read it to you?
Yeah, go ahead.
Do you hear me?
No. I hear you, but I didn't hear the question.
Okay, the question: do you think the preform pairs you mentioned are bond pairs or scattering pairs?
Well, the data cannot say one way or another. I don't know. I don't know what we have done, which is not published.
Another question about magnetoresistance. How the behavior depends on the direction of magnetic field. What is the field dependence on the whole conductivity of the whole resistivity? Sorry.
The whole resistivity is linear in field. The field dependence has not been really studied very much. There is one data point or one report which comes from Nigel Hussey's group, and then we have our own unpublished data, but I'm afraid only on one doping level. And both of these showed that there was no difference whether the field was parallel or perpendicular, and that seems to rule out the orbital origin. It looks like it comes from spin.
Okay. So let's thank again Ivan for a very interesting talk. Thank you so much.